So in the last video, we looked at what the displacement was using the position time graph, showing that it started at the 0 position and actually ended at a position of 5 meters to tell us that it had 5 meters of displacement in the positive direction. Well, is there some way we can find out what the displacement is using our velocity time graph? And indeed there is. So what I'll do now is show you how that might happen. So if we look at the velocity time graph, I'm going to make a little rectangular box here. And then shade that in. And so I'm curious now what the dimensions are of this box we just made. And it looks as though we have a value of 7.5 meters for every second, which again was our velocity in the first segment. So a 7.5 meter for every second height for this box, and a width that is the size of 2 seconds. So we'll write that down. We have a height of the box of 7.5 meters for every second, and we have a width of the box of 2 seconds. Now, that means that the area of that box can be found by taking 7.5 meters for every second times the width of the box, which is 2 seconds. Now when that's done, the unit of seconds cancels, and we have 7.5 meters times 2, which is 15 meters. Now, if you'll remember, back at the position time graph, during the first 2 seconds, how much change in position was there? How much displacement had the object experienced? And we see that it experiences 15 meters of position change during the first 2 seconds, which is now verified with what we see on the velocity time graph. Because what ended up happening, we took the velocity value, 7.5 meters for every second, times the time interval over which that velocity occurred, which tells us that a position change equals the velocity that you traveled times the time interval over which that velocity took place. And those then are the dimensions of our rectangles that we see on the velocity time graph. So if we continue then, we see during the third second, from 2 to 3 seconds, we have 0 velocity, and therefore 0 would be our displacement. And if we then look at the last segment, and we make our little rectangle, we see we have a value of -5 now for the velocity. So we have a -5 meters for every second, and we have that over a 2-second time interval. So now we say that we have -5 meters for every second times 2-second time interval. Our seconds will cancel, and we have a -10 meters of displacement. So now we have a 15 meter displacement during the first segment. We have a -10 meter displacement in the last segment. Of course, we have 0 in the middle segment. And so how do we know what our total displacement is? Well, we simply add all of our displacements that we see in the graph. And so if we then, below here, we'll take our 15 meter displacement plus our negative 10 meter displacement, we have a total then of 5 in the positive direction meters of displacement. The same answer we got earlier from the position time graph, seeing that it starts at 0 position and moves to the 5 meter position. So another way then to figure out displacement by using then a velocity time graph instead of a position time graph. So there you have it. I hope that these little videos have helped you understand a little more clearly how position time graphs and velocity time graphs can tell us about the motion of an object.